So you drop an object, right, and observe that it bounces to half its original height. What conclusion can you draw? What if it bounces to 1.5 times the original height? Well, for part A, um, if it only bounces to 1/2 the original height, right, that means some energy was lost, right? So here, okay, it's dropped, then it hits here, and then it bounces back up to only halfway, right? So some energy was lost, basically, right? So for part A, right, some energy was lost, right? Um, Most likely, when it hits the ground, it energy of heat and sound pretty much gets dissipated throughout the universe when it hits there, and that's how the energy was lost. Okay, maybe air resistance, right? Okay, heat, right? Sound, etc. All right. What about part B? Okay, it is dropped here, right? And then it hits the ground, and then it bounces like you know way up here, right? So it gained energy basically. Okay, because like, what if there was some kind of like explosion that happened right at the collision point, and then like gave more energy to make it go up higher. Okay, so some kind of okay, or we could have gotten like earth like or the ground like gave a smack or something. Okay, just so I'm not going to speculate what happened, but it just gained energy, maybe explosion, right? Okay, okay, etc. All right, let's take a look at number 4. When an elevator descends from the top of a building and stops at the ground floor, what becomes of the energy that had been potential energy? Well, there must have been some work done, right? So here we have the mass of the energy, the elevator. So we have mgh, and as it comes down to the ground floor, right, your v is equal to 0. Well, there's no kinetic energy, there's no potential energy. So what happened to it, right? So there must have been work done, right, by brake, right, on the elevator, right? Because so the applied force, which is brakes, or so some work was done. So force applied, and they applied brakes onto this elevator. It would do work on the elevator to take this much of potential energy away from the elevator, and that's what's happening. Okay. All right, any questions so far? Okay, good. Next, a certain spring stores 25 joules, okay, 25 joules of potential energy when it is compressed by 7.5 centimeters. What is a spring constant? Well, you know that U of x is equal to 1 half k x squared. Come on, this is just plug and chug, right? So 25 joules is equal to 1 half times k times. Now here, 7.5 centimeter is equal to 0.075 meters, and that's what you have to use, right? So if you work it out, I think you'll get your k value to be 50 divided by this squared, and so it should be a big number. So 8.9 times 10 to the third newtons per meter. So that should be easy. All right. Number 3, you drop a 2-kilogram textbook to a friend who stands on the ground, which is 10 meters below. Right? If the potential energy is taken as being 0 at the ground level, so this is the ground level and this is where the 0 is, right? Then what is the potential energy of the book when you release it? Okay, so for part A, right, it's simply potential energy is equal to mgh, right? Therefore, you have 2 times 9.8 times the height of 10 meters, right? So I guess you get like 196 joules. All right. What about part B? What is the kinetic energy just before your friend catches it in her outstretched hands? Well, at this location here, at this location, this has kinetic energy and potential energy gravitation, right? Because it still has height. Therefore, we're going to assume there's no air resistance, okay? So for part B, right, work done by conservative, non-conservative force is equal to 0. Therefore, the total energy initial is equal to total energy final. Total energy initial, right, is right here. This is the initial, right, and this is the final. Therefore, initial, I only have potential energy gravitation initial. Here, final, I have kinetic energy final plus the potential energy gravitation final. We already know what this is. This is 196. So kinetic energy final plus potential energy gravitation is mghf. So 196, right, minus 2 times 9.8 times 1.5, okay, is equal to kinetic energy final. So if you work it out, I believe this becomes 29.4, so 196 minus 29.4, we get 167 is equal to kinetic energy final. All right. Now for part C, how fast is the book moving, right, as it is caught? Well, we know the kinetic energy final is equal to 1 half mv final squared. Therefore, 167 is equal to 1 half times 2.0 times VF squared. So VF is equal to square root of 167, and that comes out to 12.9 meters per second. All right. All right. So let's take a look at number 7. All right, frictionless roller coaster. So we have this frictionless roller coaster cart at the top of the first hill, right, with a speed v naught. What is the speed at point A, right? Now the h and h, they're same heights. So here we have potential energy and kinetic energy, and because it has v naught, right? As it comes down, it's going to gain more kinetic energy but lose potential energy. But the total energy should be the same as it started here. And as it goes up, we're going to gain the same potential energy back, right? Therefore, the speed of this at A should be exactly the same as your original V naught, right? So VA is equal to same as V naught. Okay? So that's easy. So let's work it out. So A, right? So kinetic energy initial plus the potential energy initial is equal to, because it's frictionless, right? You can say work done by the non-conservative force is equal to 0. Therefore, total energy initial is equal to total energy final, right? So kinetic energy initial plus the potential energy initial is equal to, right, kinetic energy at A plus the potential energy at A. Okay, so here we have 1/2 mv naught squared plus mgh, that is equal to 1/2 mv at A squared plus mgh. So as you can see, you could cancel that out. You could cancel out the 1/2 as well as the mass. So V naught squared is equal to VA squared. So my VA is equal to just V naught. All right. Part B, your height is only now this much, right? So for part B, you have kinetic energy initial plus the potential energy initial is equal to kinetic energy at A, not A, B, and potential energy at B, right? Therefore, 1/2 mv naught squared plus mgh is equal to 1/2 mv at B squared plus mg 1/2 h, right? So first, I guess we could cancel out all the masses, right? Mass. Okay. And then, if you were to bring this to this other side, so you have 1/2, right? V naught squared plus GH minus 1/2 GH is equal to 1/2 V at B squared. If you multiply both sides by 2, right, well, this becomes 1/2, right? So you get 1/2 V naught squared plus 1/2 GH is equal to 1/2 VB squared. So all the halves can cancel out. Okay. So V at B is equal to square root of V naught squared plus GH. All right. And then for part C, how high will it go on the last hill, which is too high to cross, right? So for part C, I want to know how high, right, this final Y position is going to be, right? Oh, I forgot to do this part. Sorry. Sorry. For part C, and how fast is going at point C. So kinetic energy initial plus the potential energy initial is equal to kinetic energy at C plus the potential energy at C. Potential energy at C is 0, it looks like. I don't have any height at C. I don't have any height at C. So this potential energy at C is 0. So 1 half mv naught squared plus mgh is equal to 1 half mv at C squared. So again, all the masses can cancel out nicely. Right? And if you multiply 2 to both sides, right, you get v naught squared plus 2gh is equal to vc squared. So vc is equal to square root of v naught squared plus 2gh. If you look at this equation should look familiar to you. This is equation number 3 in kinematics from your summer assignment. Remember, Vf squared is equal to Vi squared plus 2a delta x. Very similar thing, isn't it? Yeah. All right. So this is C. Now for D, how high will it go? Right, for D. So here I have kinetic energy initial plus the potential energy initial is equal to kinetic energy at D plus the potential energy at D. But kinetic energy at D will be 0 when it reaches the maximum height. You'll come to an instantaneous stop before it starts to roll back down again, right? So here, 1 half mv naught squared plus mgh is equal to, this is 0, so this is mgyd, right? Therefore, you can cancel out the masses again, right? And if you were to divide both sides by g, right, your y at D is equal to, right, V naught squared over 2G plus H. So this is how high it's going to get at your Y final. Okay? Is that good? All right. Now let's take a look at 11. Figure 8-25 shows an 8 kilogram stone, right, resting on a spring spring is compressed to 10 centimeters, right, by a stone. A. So here, this is your equilibrium point, right? X naught, right? And then it's compressed to this much, right? When you put the stone on it. So this is at this point is without stone, right? Without stone. And then when you put the stone on it, it compresses this much, okay? And the mass of the stone is equal to 8 kilograms. Okay, so this is actually like the equilibrium position with the stone spring system. Okay, so um, I think we should try to figure out what the K value is. Huh? It'd be nice to figure that out. So let's do that. What's compressing the spring? What force? Well, there's only one force acting on this spring, and that force is basically Fg, right? So Fg is compressing this. And this, at this point, we have Fg is equal to your spring force going this way, right? So F spring, and this is your Fg, right? So if we were to think about spring here, F spring is equal to negative Kx, right? But I just want to find out what I'm not worried about the actual, the distance or the direction of this. So let's just look for the magnitude of my F spring, okay? And this are equal to each other, right? This is basically Fg. So that is equal to, right, Kx. So Fg is actually, right, 8 times 9.8, and that is equal to K times X, which is 0.10. So my K value for this spring comes out to 784 newtons per meter. That's the K value for the spring. All right. So that's part A. B. The stone is pushed down additional, right, 0.3 meters. Now this thing is being loaded even more, right? So now, how much, right, energy does it gain? The potential energy, right? So not only did it compress zero point 0.1 meters, now it's compressed even more with 0.3 meters. So total compression happens to be, right, 0.4 meters. Okay. So if we consider this to be our zero, so here's our zero, instead of here, right, because we don't know what the length of the spring is, so this is probably easier if we make this our y is equal to 0 here. Okay, so potential energy gravitation here at this point is 0. Okay, kinetic energy here is 0. Okay, because it's not moving, because it's compressed and it's not released yet. Only energy that I possess at this point is just potential energy of spring. Okay, and potential energy of spring is of course 1/2 kx squared. Therefore, right, 1/2 times k, which is 784, times x. X is 0.4, right? 0.4 squared. So if you work it out, I guess you'll get something like 62.72 joules. That's how much the potential energy, right? And here, potential energy gravitation is equal to mgh, and that is 8 times 9.8 times 0, so it is 0 joules for potential energy. Okay. Now, for part C, how high above the release position will the stone rise? So from here, when you release it, it's going to go boing, and then it's going to go up all the way up to here before it slows down, and stops instantaneously before it starts to drop back down again, right? So at this point, the kinetic energy is 0, right? And so here, my V at B is equal to 0. Therefore, the kinetic energy at B is equal to 0. Okay? So they want to know how high it gets. Okay? They want to know how high it gets. So we're going to assume, well, this is part B. For part C, we're going to assume there's no air resistance, right? There's no work done by non-conservative force, right? Therefore, total energy initial is equal to total energy final, right? So here, kinetic energy at A plus the potential energy of spring A plus the potential energy of gravitation A must equal to kinetic energy at B plus the potential energy of spring at B plus the potential energy gravitation at B. Well, some of these are going to go to 0 because it's not going to exist, right? So at point A, right here, I have no potential energy gravitation, right? So this goes to 0. It starts from rest because it's released from rest. So the kinetic energy at A is 0. So the only thing I start with is the potential energy of the spring. Now let's take a look at point B. When it reaches the maximum height, it stops instantaneously, so the kinetic energy at point B is 0. Spring's not attached to this anymore, so there's no spring involved at point B, so there's no potential energy of spring whatsoever. My classroom light just got turned off. I hate when this happens. All right. So only thing that I have up here is potential energy of gravitation at B. Okay? Therefore, notice how these go to zeros and these two are the only one remaining. So here, potential energy spring at A, we already know what that is, right? This is 62.72 is equal to, right, mgh. So 62.72 is equal to 8 times 9.8 times h. So if you solve for this, I believe your h comes out to 0.8 meters. All right. Let's go a little further than this. how fast is it moving at here, at D? So for part D, what is V at D? Let me see if you guys can do that. I'll pause this for about 5 minutes and then see if you can calculate how fast it will be moving right here at D. All right, let's take a look. Well, we know at D, right? At D, we could compare this as our initial again, right? Which is total energy initial is equal to total energy final. Initially, I only have potential energy of spring at A, right? We already established that. At point D, I definitely have kinetic energy at D plus potential energy gravitation at D, and I have potential energy of spring at D. Okay? I'm running out of room here. So if you work it out, okay, I have 62.72 is equal to 1/2 times 8 times V at D squared plus, right, 8 times 9.8 times 0.3, right, plus 1/2 times K, which is 784 times 0.1 squared. So I have to solve for D. So hopefully you guys got V at point D to be somewhere around 2.97 meters per second. Is that okay? Did you guys get that? Good. So you should be able to calculate speed at any point along this path, right? Doesn't matter. As long as you know where the height is, the position is, you should be able to calculate the speed of it at any time. All right? All right. Moving on. All right. A ball with mass m, so this ball has mass m, is attached to the end of a very light rod, so this is the rod right here, with length L, and negligible mass. All right, so it's a very light rod. The other end of the rod is pivoted so that the ball can move in a vertical circle, so it's going to be able to go this way. The rod is held in horizontal position as shown in figure 8-26. And then, given just enough downward push, okay, so it actually is given a little shove, so that ball swings down and around and just reaches the vertical upward position. So if I just release it instead of giving a shove, most likely it only has enough energy to go to the other side and come up to here before it comes back down again. But if I give a little downward push, if I give it a little shove, then it has more than this potential energy to go around and even more to up to here, right? At this position, my V final is equal to 0 at this position, okay? What is the change in potential energy of the ball? Well, that's easy, right? So here, if I were to consider this to be my zero, this height here is L. And this height is 2L. Okay? So for part A, what is the change in potential energy? Change in potential energy is potential energy B minus the potential energy at A. And that is, right, mgy final minus mgy initial. Therefore, mg2l minus mgl, that is then mgl as my change in potential energy. Right? So notice, right, path traveled, right, does not matter. Right? Just endpoints, okay? Oops, just endpoints matter. Okay? So all this path doesn't mean anything. It's just where do you start and where do you end up? Okay? And how much height has changed. Now, what about part B? What is the initial speed given so that it reaches up to there? Right? Well, again, if we were to say there's no work done by friction, so work done by non-conservative force is zero, therefore the total energy initial is equal to total energy final, right? So initially, I have kinetic energy at A plus the potential energy at A. That's gravitation, by the way, because there's no spring here. And that is equal to, right, kinetic energy at B plus the potential energy at B, gravitation, right? Well, we already established that speed is zero at the point B, so the kinetic energy at B is equal to zero. Here, I have 1/2 mv at A squared plus mgl is equal to, right, mg2l is the potential energy at point B. So, we know the masses can all cancel out nicely. If I bring this to the other side, I get just GL, because 2GL minus GL is just GL, right? And then, if I bring the 2 to the other side, I get 2, and then I get VA squared. So my V at A is equal to square root of 2GL. All right? Next. All right, this looks trouble. This looks like a trouble here, but we could get this done. So here, we have 2 kilogram block is placed against the spring on a frictionless, right, 30-degree incline. Now, frictionless means, again, That means work done by the non-conservative force is equal to 0. And therefore, we can use the total energy initial is equal to total energy final. All right. Therefore, the spring constant is equal to, we have 19.6 newtons per centimeter. So be careful with that, right? And it is compressed 20 centimeters. Now we're going to be working with potential energy gravitation too, because it's going to gain height. And if you're going to work with potential energy gravitation, you know your G is going to be measured in 9.8 meters per second squared. And if you have centimeters here and centimeters here, that's not going to be good. So my recommendation is convert these into the proper units. So I can say, right, K is equal to, just multiply this by, 100, right? So you get 1,960, right? That will be a proper newtons per meter. And this X is equal to 0.20 meters. Okay, so from here to here is 0.2 meters. Okay, this is our zero. This is my y is equal to 0. Okay, this is the height. This is the height that block will gain once it's released. Okay, you don't have to worry about all this in between. Okay, so since we have established that total energy is equal to total energy final, right, we can say, right, the total energy at A must equal to total energy at B. Okay, so initial, final. At A, I have potential energy of spring at A. It's not going to be moving, so the kinetic energy at A is 0. Potential energy gravitation is also 0 because we considered our A to be our 0 height. So this also goes to 0. Now at B, I definitely have potential energy gravitation at B. Potential energy of spring at B doesn't exist because spring doesn't come into play. Because spring only is going to just launch it, but that's it. There's no spring here. When it reaches the maximum height here, right, what happens? When it reaches maximum height, it stops. So the kinetic energy at B is also equal to 0. Therefore, we can actually start working on this. Okay. Let's see how high it gets. So here I have 1/2 kx squared is equal to, right, mg h. Therefore, I have 1/2 times 1960 times 0.2 squared is equal to, right, 2 times 9.8 times the h. So what's my height? Well, let's calculate that. So here we have 0.5 times 1960 times 0.2 squared, and I get 39.2 is equal to, right, 19.6h. So divide that by 19.6, and my height is equal to 2 meters. But that's not what they're asking for, right? What they're asking for is how much distance it travels. This is what they're looking for right here, right? He called it y here. So if we know this is height and this is y, we know this is 30 degrees. So height happens to be 2 meters. So we know sine of theta is equal to h over y. So y is equal to h over sine of theta. So y is equal to 2 over sine of 30, and therefore that is 4 meters. All right. Good. That wasn't that bad, right? It looked, oh my God, but yeah, it's 4. All right. All right, all right, all right. Number 19. We have, right, a 50-gram ball. This is 50 grams. So the mass is really 0.050 kilograms. And it's thrown from a window with initial velocity v naught of 8 meters per second. So this v naught is equal to 8 meters per second. Remember how we used to actually, like, break this up into VIX and VIY, and this is 30 degrees, right? Still not a bad idea, I guess, right, to know that. So you know that this can be changed into VIX, and then this is the VIY, and this is 30 degrees, right? So let's take a look what's going on. Using just energy methods, determine A, kinetic energy of the ball at the top of the flight. So they want to know what's going on at the top of the flight. What is the kinetic energy at here? At this location, I only have the Vx, Vy is 0 at this point, right? Well, how can we calculate the Vix? This Vix and this Vix are the same, right? So Vix is equal to V naught cosine of 30 degrees, right? Therefore, it is 8 times cosine of 30. So my Vix comes out to 6.93 meters per second. Therefore, for part A, right, the kinetic energy at top, right, is equal to 1/2, right, mv squared. And that is equal to 1/2 times 0.050 times 6.93 squared. And if you work that out, I think you'll get something like 1.2 joules. Okay. What about part B? Its speed when it's 3 meters below the window. Well, we know there's no work done by air resistance, right? This is being done at vacuum, so let's understand that first. So work done by non-conservative force is 0, therefore total energy initial is equal to total energy final. Okay, that's given. So here, initial, here, final. Okay, so we could say initial, final. So for part B, we know total energy initial at A is equal to total energy at final, which is B. Okay? So we have kinetic energy at A plus the potential energy gravitation at A. There's no spring here, so we're not going to have spring potential energy. That is equal to kinetic energy at B plus the potential energy gravitation at B. Well, since we're going to consider this to be our 0 at final location, which is 3 meters below the starting point, our potential energy gravitation at B is 0. However, I do have kinetic energy here, which is 1/2 mv0 squared. And that v0 is 8, because we're looking at just speed. Okay? And plus mg at HA, right? And that is 3 meters. That is equal to 1/2 m at VB squared, right? This is B. So first thing is first, all the masses can cancel out nicely. And if I multiply 2 to both sides, guess what? I get the third equation, the third kinematics equation, right? So V0 squared plus 2GHA is equal to VB squared. Well, V0 is 8, so 8 squared, right, plus 2 times 9.8 times 3 is equal to VB squared. Hopefully you can solve that. What do you get? So you get minus 2 times 9.8 times 3, right? Plus 64. So square root of that. And I get VB is equal to 11.1 meters per second. All right. I guess with correct sig phase it's just 11, but I'm not worried about that. All right. Let's take a look at, does the answer to B depends on either mass of the ball or initial angle? Well, what do you think? Does it depend on the angle or the mass of the ball? Well, look at that. We canceled out all the masses, right? So V at B does not, right, depend on mass or angle, right? Just V naught and H. And because kinetic energy is a scalar quantity, any energy is actually a scalar quantity. You don't need to have direction. As long as it has that speed, that's all you care about. Okay. All right. Maybe one more. All right, 22. No, 23. Right? 23. Here, I have the string in figure 8-31 is 120 centimeters. So the length of the spring is basically 1.2 meters. And the distance D to the fixed peg is 75 centimeters. So this right here is 0.75 meters from here to here. Okay. So this R, the radius of from here to here, happens to be 1.2 minus 0.75, and R then is equal to 0.45 meters is my R. So as this comes down, the string is going to get caught onto this peg, and it's going to make this loop, and this is going to be a smaller circle within this bigger circle. Okay. So when the ball is released from rest, so initial velocity at A is equal to 0. That means kinetic energy at A is equal to 0. Right? It will swing along the dashed arc, right? How fast is going at A when it reached the lowest point of the swing, right here at B. Okay, so they want to know what's going on at B. So for part A, again, we're going to assume no work done by non-conservative force. Therefore, total energy initial is equal to total energy final. Therefore, total energy at A must equal to total energy at B. Total energy at A. Well, we could write down, there's no kinetic energy. I mean, I could write down all those three energies here and start canceling them out to zeros, but we only know that potential energy of gravitation exists at point A. Okay? And at point B, I only have kinetic energy at point B because there's no spring, first of all. And potential energy at B is 0 because Y is 0 at point B. I hope everybody can see that. Okay? Therefore, I have mgl is equal to 1/2 mv at b squared. Right? So, notice what happens to the mass. Mass will cancel out nicely. Right? So Vb is equal to square root of 2gl, or if we were to plug it in 2 times 9.8 times 1.2. Okay. So what do we get? I get my V at B is equal to, get 4.85 meters per second. Okay. Now, what about B? When it reaches the highest point after the string catches on the peg. So they want to know what's going on at C. Right here. So for part B, right, total energy. Now you could consider total energy initial to be either at A or at B. It doesn't matter because total energy is going to be same no matter where it is. And if you already know, right, what this is, you could use A, right? So total energy at A is equal to total energy at B, which is equal to total energy at C. You pick and choose. I want to do it A to C rather than B to C, okay? So I'm going to say MGL, right, is equal to total energy at C. I have kinetic energy at C, right, plus potential energy at C. Okay? Hope everybody got that. If you want me to rewrite this, you could say uh, kinetic energy at A plus potential energy gravitation at A is equal to kinetic energy at C plus potential energy gravitation at C. This is 0. So MGL is equal to 1 half MVC squared plus, right, MG2R. All right, so hopefully you can see that. So now, notice the masses will cancel out again, right? And if we solve for VC, right, we should get VC is equal to, right, square root of, right, GL minus 2GR whole thing times 2, right? So that is equal to square root of 2 times 9.8 times 1.2 minus, right, 2 times 9.8 times 0.9. Oh, sorry, no, 0.45. All right. So what do we get? All right. So here, so here, 9.8 times 1.2, and I get 11.76 minus, right? I get 8.82, right? So times that by 2. So I get square root of 5.88, which is equal to 2.4, 2.4, right? 2, 2.42 meters per second is what I get. Whew. All right. I think I'm going to stop there because I don't think I have enough time to do another problem. So you should continue on with this. Page 9, okay. Page 9 is actually a good problem. Okay. You would have done a lab with a cannon shooting this thing straight up and doing this lab. But since we can't do a lab, this will be a good problem to do to understand and check your understanding. All right. I'll stop the lecture here.